Next, we would like to look at the issue about soft margin. In the SVM, sometimes it is possible that the data that we are trying to classify, and we classified using the boundaries. Okay. It is possible that sometimes you want to allow that there are some errors inside, this area. Okay, maybe you have like data points here, and okay, if they are so easily classified, then they're all very simple to be classified. But sometimes maybe you want to allow that there are some errors on this side, or the error from another class on the other side. Okay, so this is what is related to what is called soft margin. And so in the SVM, what they do is they try to introduce what is called the slack variable. Okay, let's call it sigma I. So sigma I is in one way is related to like errors. Okay, and when we do this, similar to the example that we looked at last time, so we're trying to minimize, the cost function, right? So in some way, with this type of slack variable, we can minimize the cost function. Okay, but then we added another term related to these additional errors, and we also multiply with the variable called c. Okay, this c variable is it is often known as regularization term. Okay, and this c is a constant that multiplied the all the additional errors. Okay, and to the power of k. Okay, and typically k is either 1 or 2. Okay, and we minimize it subject to the condition that yi of w, let me put in the vector term, w transpose multiply with xi plus b greater than or equal to 1 previously, right? And then here we will put in minus sigma I. So this is like the additional errors, okay, where sigma I is greater than or equal to 0. Okay, so then when we put this into so equivalently, when we simplify it using similar approach as before by putting in the Lagrange function with the alpha variables or the Lagrange variables, okay, then we will have L of alpha equals to summation of alpha I, okay, still the same approach, minus 1/2 summation I summation j alpha I alpha j yi yj and xi xj, okay, and then subject to the condition that alpha I is greater than or equal to 0 but less than or equal to C. Additionally, summation of alpha I yi is equal to 0. Okay. So if you don't follow these, please go back to the previous lecture and look at the simple case that we looked earlier. Okay. So the solution to this, also similar to what we had before for the simple case, we'll have that W is going to be equal to summation of alpha I, yi, and then xi. However, a slight change is in the bias term where we have yk multiplied with 1 minus sigma k and minus W matrix transpose times xk. Okay. And here, this k, actually let's call capitalize k. Okay. This k is the index of the largest alpha k that we can compute, that we have. Okay. So it's quite similar to what we had before, but we just added up, we just put more terms into it. Okay. I'm not gonna put example here, but it will be similar to what we had before. Okay. And also you can sort of speculate that in the Lagrange function, so if you have more terms, actually here's the I think it's okay. So next topic, we want to look at the nonlinear SVM. Okay. We have often heard of nonlinear SVM that when we do training for the data set using SVM model, we can select to use either linear or nonlinear, right? So what is the idea of having nonlinear SVM? So basically, we're trying to map data points that we have to higher dimension. Okay, so that it is easier for classification. Okay, for example, what? Let's say that we have this type of data sets that looks like this. So we have this data set in the 2D space, right? And maybe they look like this. Okay. So you can say that, hey, can I do classification of this data? So if you look from this picture, maybe you think that, okay, how about I have like the boundary like this? Okay. Which is true. Okay. But when we do this, for the nonlinear SVM, what they do is they want to transform this type of nonlinear, pictures into a linear type construction. Okay. And one way, if you consider the picture on the left-hand side, maybe you can find that all the values that are in the circle, they will pull together somewhere here, whereas the plus data points, they'll end up on the other side. Okay. for example, and then it becomes more linear, as we look at it. So in a way, what we do is we have a certain function to transform the original data, let's call this is x, right, into the new features, okay? And generally, we map to higher dimension to do this, okay? Well, however, to map this, this type of transformation function can be quite difficult to find. Okay. So in general, what we look at is we look at what is called a kernel. Okay. We use the concept of kernel for this type of transformation. And kernel is what is called similarity function. Okay. Let's look at an example. Let's say that we have this phi function of the transformation, okay, where x is equal to x1 and x2. Okay, let's say this phi function is x1 squared, x2 squared, and then square root of 2 x1 x2. You can write this in terms of vector as well. Okay, that's fine. And this will be 3-dimension instead of 2-dimension as previously. Okay, so in a way, phi is a mapping from 2-dimension to 3-dimension. Okay. A kernel is often defined as like this. If we have kernel of 2 points, say x and z, okay, so these are 2 vector points, okay, so the kernel is defined as the inner product of phi of x versus phi of z. Okay, so this is like a inner product. So in essence, if we look at from the previous, the above example, so we will have this is inner product of x1 square, x2 square, and then square root x1, x2. And for phi of z, we have z1 squared, z2 squared, and then square root 2 of z1 and z2. Okay. You can write each one as vectors as well. So when you do inner product, it's just multiplying each element twice and then sum together. Okay. Or if you do the if you do the bracket has to be outside, no, just to avoid confusion. And or if you write in terms of the vectors, you have to do transpose, and then one is the column multiplied with the row. One is the row multiplied with the column. Okay. So in essence, it's the multiplication of element by element and then sum together. Okay. So what you have is just x1 squared, z1 squared, plus x2 squared, z2 squared, okay, and then plus square root 2 times square root 2, you get 2, and then you get x1, x2, z1, z2, okay. So if you do this, what you get is, so this term is actually just x1 z1 plus x2 z2 squared. Okay, you can expand it if you don't see it first time. Okay, and so you can write this as the inner product of x1 x2 and z1 z2. Okay, and the whole thing is squared. Okay, or you can write this kernel function, kernel of x and z, as the inner product of x and z, and then squared. Okay. So you can see that when we have this mapping function, so for any two data points, okay, we can compute the kernel as the inner product of this phi function. And now it looks like it's it looks different, right? Okay, and this is the type of when we use the nonlinear function, there are various types of example of nonlinear function that we can use. Okay, so in general, what are the example of the kernel function? Okay, the simplest possibility for the kernel function is just the case for the linear case. Okay, so for the linear case that we have looked at before, so this the kernel function is just xz. It's just for any two data points, it's just the inner products xz. Okay, or if you write in terms of the vector, it's just x transpose times z. Okay, then if you look at polynomial, okay, we don't use polynomial very often. Okay, and we'll show you why. So for the kernel function of polynomial, you have the kernel function of some variable a times inner product x and z plus another variable, and then raised to the power, say b or beta. Okay. For number 3, this one is used quite often. It's called Gaussian kernel function, but some people call it the radial basis function, or RBF, So for this type of function, so the kernel function x and z can be computed from, Gaussian function. So it's e to the negative some variable size of x minus z, the whole thing squared. Okay, where the magnitude of x minus z square is just x1 minus z1 square plus x2 minus z2 square plus etc. until xn minus zn squared. Okay, and lastly, actually there are different kernel function. Yeah, and the fourth one that is also seen quite often is called sigmoid function. Okay, for this one, the kernel function is k of xz is equal to hyperbolic tangent. This is not just tangent, it's hyperbolic tangent of x of a times inner product x and z plus b, okay, where the hyperbolic tangent function of any value, say x, is e to the x minus e to negative x divided by e to the x plus e to negative x. Okay, there are also some other kernel function as well. Okay, so because inner product so what's the meaning of kernel function? I think it's best to look at this case, which is the Gaussian type. Okay, so if you take a look here, so any data points like x and z, you know, if they are near each other, okay, when you use the Gaussian function, okay, what you will have is you have large value of k, or the kernel function. Okay, and so what are the shapes of this nonlinear function that we look at in these four cases? If you look at the linear case, it's quite it is quite simple, because if you have data, say you have data that scatter like this, let's say there are three types of data that scatter. Okay, so for the linear type kernel, you just divide into three linear type areas. Let's call it A, B, and C. Okay, if you look at like polynomial, okay, you may have the boundary like this. So it's curvy, like polynomial function. Okay, if you have like RBF, okay, you may have something that's more of like more circular boundary. If you have sigmoid is not always so good. Sigmoid, because it's hyperbolic, they are like a curve as well. You may have something like this, A, B, and then C, you know, something like this. So very often time you find that we use RBF quite often. Linear is not bad actually, yeah. But for polynomial, maybe it doesn't reflect your boundary so well, okay. And if you remember last time, we also talked about two parameters. One is the C, regularization, right? So also the gamma as well. Okay, so both C and gammas, they will, for the C, it allows for more errors, right? But for gammas, it allows for more curvatures. So if you have like circle and you have lots of curves in it, yeah, then it's related to the gamma. Okay. And this gamma is actually, when you look at RBF, I think it's related to this, the square that we look at. Okay. Also, okay, last thing I want to talk about is what is called multiclass SVM. Okay, so far we have been looking at the SVM from the binary point of view, okay, but we can modify the SVM for multi-class type classification. Typically, there are two approach. Okay, one is called one versus one, or OVO. The other one is called one versus the rest, or OVR. Okay, so both are the method that can be called heuristic method. Heuristic means it's just a rule based. Okay, and what are the strategy when they do multi-class SVM is to build many models. Okay, and then output as some probability values, and then use that for decision. Okay, for example, if you look at the first case is the OVO, or one versus one. Okay, so what do we do? Okay, also when we say build many models, meaning that we build many models of the binary classifiers. We build many of them. Okay, so let's say if you look at one versus one, so what do we do? Well, I mean, the name is very obvious, right? We build model of binary classifier of one class versus the other class. Okay, so let's say that we are given that we have 4 classes, like class A, B, C, and D. These are the classes that we want to classify. Okay, so what do is we need to build the SVM of A versus B, A versus C, A versus D, and so on. B versus D, and lastly C versus D. Okay, so, and in this case the number of binary model is going to be equal to number of class multiply number of class minus 1 divided by 2. So for example, in this case is 4 times 4 minus 1 divided by 2, which is 6. Okay, because we have data for each class already, right? So we group this data, we build model for each 2 set at a time. Okay, also second type is called one versus the rest, one versus rest. Okay, or sometimes people call it one versus all. Okay, so what do we do if we have, like in this case of A, B, C, D, 4 classes, and each class has its own data set? So we first build A versus the rest, which is B, C, D. Okay, then we build another one, which is B versus A, C, D, C versus A, B, D, and lastly D versus A, B, C. So here we only have 4 models. Okay, so here the number of models that we build is just number of class. Okay, so what we do is, once we build a lot of these binary classifiers, we will output what is called membership probability. Okay, and then we predict a class based on this probability value. Okay, so I think this is it for SVM. And last time I also gave you some Python function that you can play with using SVM. But generally for the SVM in Python, it's in the function SVC, right? In there you can already plug in, you can already put the option of linear or what type of nonlinear, which type of kernel that you want to use. Okay, and I think that's about it for today.